11 toys went into space. The 10 that were selected by the astronauts packaged aboard the Space Shuttle Discovery, and an 11th toy selected by Senator Garn. And this is the paper airplane, a simple toy that you can recreate on your own that will fly on Earth and maybe fly in space. The first thing we discovered about a paper airplane is that it is elegance in motion in space. There's no gravity to pull it down. All it needs is an aerodynamic shape, a little shove, and off it goes. Questions that were asked by kids about paper airplanes: 1, would it fly as well backward as forward? Since there's no gravity, if you take the airplane and push it backward, what would happen? We discovered, in fact, a backward flying paper airplane doesn't fly at all. So even though there's not gravity in space to worry about, anything that flies needs to be aerodynamic. It needs to move through the air because there's still air in space. To illustrate this, we also just asked Senator Garn to take the airplane and let it go and watch it as it moves in the cabin. You can see by its motions and floating around that there are air currents that affect the motion of an airplane. Another idea, maybe in space you could take a paper airplane and push it against a wall. What would happen to it? On Earth, of course, it crashes against the wall and falls down by gravity. In space, it just, like a ball sort of, bounces off the wall and comes back. Maybe, perhaps, you could take a paper airplane and instead of throwing it forward, you could blow it forward, producing your own air current to carry it through the cabin. And in fact, because there's no gravity to pull the airplane down, just a gentle breeze caused by your breath will float the airplane very nicely. Besides gliding straight, we wondered if an airplane, given a slight tilt when it is tossed, would actually do a banked curve. And in fact, even this could be performed in the zero-G environment of Space Shuttle. So like the regular toys, the paper airplane that you make right here in a classroom or at home will fly better in space than it flies on Earth.
One of the items that we wanted to investigate the behavior of in space, which we anticipated might be slightly different at least than in one gravity field, was a paddle ball, a rubber ball suspended from a piece of elastic with a wooden paddle. And of course, in one gravity, here on the surface of the Earth, there's a certain technique that must be mastered in a way of timing hand-eye coordination in order to make this work. For instance, of course, if I let go of the paddle ball, it's going to drop to the ground. If I pull it apart and let go, the ball may smack the paddle once and immediately drop down, but in fact, as you can see, what happens is it actually misses the paddle. We might compare this to what you think might happen in zero-G. Will it still miss the paddle? We'll see a little bit later on. So we'll try that once more here with letting go of the ball. Sure enough, it misses the paddle again. How about a vertical orientation? Will it hit the paddle this time? It may depend on how far I stretch it and whether I let it go straight up or not. One hit, but then a dangling around. We can suspend the paddle from the ball, of course, in various manners, investigating the dynamics of that sort of thing. Or the ball from the paddle and investigate the dynamics of that, which we just looked at. We could, of course, let them both go in one gravity, and of course, as you just saw earlier, they would fall to the ground no matter how far I stretch them apart. So there's no point in doing that here. What we should interest ourselves in is, though, a vertical orientation, perhaps a horizontal orientation, and the normal paddle ball toward the deck kind of orientation. So if I operate the paddle ball in this sort of direction, in this sort of manner, which is kind of a 1G operation, I should be able to do the same thing in 0G. Operating it this way, however, is a little bit tougher task in the gravity field, because not only is the ball being pulled down by the elastic strap, but it's also going to fall down due to its weight and the force of gravity. So let's try that. Much harder to do. One more time. Still much harder to do. Horizontal orientation, you might suspect, depends upon the force of the elastic cord pulling the ball back toward the paddle in this kind of direction. Compare this sort of information to what we see in zero gravity with the paddle ball. The paddle ball in zero gravity is probably going to behave somewhat differently in that I don't have to pull it back with nearly the force that I have to pull it back and smack it rather hard like I do in a one gravity field to make sure I get enough extension of the elastic in order for it to pull it back against the paddle and pull it back so that it hits the paddle instead of pulling back and dropping below it like it does in one gravity. We should attempt to pull it apart and let go to see what happens, and during a paddling exercise perhaps let go of the paddle to see what kind of dynamics that the system is going to experience in the absence of gravity in orbit.
The slinky did some pretty interesting things in zero gravity, but nothing totally unexpected. I think we were pretty sure that it is gravity that helps a slinky to slink. If you've ever played with a slinky, you know it will go down the steps, but it uses gravity as it does that. As you can see here on the ground, if you release the slinky, it flips over and it actually steps down the steps. It uses its spring forces to actually flip over, but then it counts on gravity to pull it back down to the next step. Of course, in zero gravity, you cannot make the slinky walk downstairs because there is no gravity. But it does still retain its spring forces so that when you actually pull the slinky down like this, if there's no gravity on this end, it still has some spring forces that actually will pull it back this direction because it does have its spring force in the absence of gravity. This sort of thing, when I use my hands to simulate gravity, I'm pulling down on this end, pulling down on this end. I can do that in zero gravity simply because, once again, I'm counting on my hands pulling rather than gravity tugging on one end or the other of the slinky. Another thing that we postulated would happen in zero gravity that in fact did, if you stretch the slinky out, you're tugging on it and it has its elastic and spring properties, that if you release both ends, the spring forces will tend to pull the ends in together. But of course there is some force when the thing comes back together that will tend to make it turn around there as it floats in space. We did some wave forces in zero gravity and found that indeed the waves act pretty much the same way. They're reflected from end to end. You can make standing waves, you can make compression waves back and forth. The one thing that it does here on the ground that it didn't do in zero gravity is sag like this. Here on the ground you can't make it form a completely straight line because gravity acts on the central portion of it that's not being held. In zero gravity, of course, we could stretch it out to a great length and still have it form a completely straight line so that we could demonstrate the standing waves and the compression waves in a much easier way.
But basically, every system like this, a spring system, it's like an oscillator, it has a certain fundamental frequency, which you can see 1, 2, 3, 4, and if I put in energy at just the right frequency, I can get it to go in that fundamental frequency. If I make it a little bit longer, that you notice it's now a little bit slower because I've made it a little bit longer. Now, if I go at exactly twice that frequency, 1, 2. Now I'm going to go twice. 1, 2, 1, 2. In space, since you didn't have the sag caused by gravity, you could have a real long slinky held out all the way, and you could get very nice wave patterns going. And the wave patterns that we saw in space were really much better than what you can do on the ground. Pushing the slinky in and out with the speed being determined by the springiness of the slinky, it was almost like working a yo-yo, and the slinky really operated like a yo-yo. Here, obviously on the Earth, I can only do it up and down. Now, speaking of yo-yos, we did find out that certain toys in space were incompatible, and if you have a slinky going out in one direction in the cabin and a yo-yo coming in another direction, you've got to be very careful, because of course if the yo-yo gets caught in the slinky, you'll get all sorts of catastrophic results. Space.
I'm Ray Seddon, and one of the toys that I played with in space were a ball and jacks. I played a lot of jacks as a little girl, and it was a fun game, and it was reasonably easy to do. I had practiced before we went into space, but I knew that it would be quite a bit different in the zero-gravity environment that it was here on the ground. The first thing that we learned was that it was very difficult to keep the jacks all in one place. As I opened my hand, here in one gravity, the jacks all stay right there quite nicely. But just the pressure of my hand against the jacks in zero gravity, if I opened my hand rapidly, the jacks went in all directions, and they were very difficult to find. So we had to do some practice on releasing the jacks very carefully, and of course, instead of staying in my hand in zero gravity, they would stay floating in midair. We also noticed that they did not tend to stay all in one small area, but would tend slowly to drift apart, so that you had to play the jacks rather quickly so that they would all be within your reach by the time you picked up the last jack. Another thing that I noticed in zero gravity, if you've played enough jacks, your timing is that you throw the ball up, then it gives you time to pick up the jack as the ball comes down, bounces off the ground, and then you grab it as it comes this way. I found that when I threw the ball upward in zero gravity, instead of coming back down and bouncing off the floor, it would continue to go up, bounce off the ceiling, and then I had to catch it as it was coming downward rather than going up. But I found still that my timing was such that it was easier for me to toss the ball up, even if I had to remember to catch it as it came back down this way. We found that one of the very difficult things to do in zero gravity were what we call 12Zs. In other words, let the jacks go, bounce the ball, and gather all the jacks up at one time. Because as you release the jacks, they tended to float so far away that by the time you went back to grab them, they were quite well dispersed. And so it took a good bit of practice to gather them all up in one handful. That's pretty easy to do here on the ground. If you release them into a small area, they'll stay there, and then when you go to pick them up, it's a fairly easy trick to pick them all up in one handful. I found it rather difficult to throw the ball downward and then try to come back and grab a jack that was floating in midair. One of the things that we found, of course, is the jacks float. If there's any disturbance, if you knock the jacks with your hand, they fly off in all directions. If the ball comes back up and hits the jacks, they fly in all directions, and they're very difficult to find. One of the other things that we did, of course, with one of the jacks was to display that it also has gyroscopic properties. You can spin it, and it would maintain its orientation the way a gyroscope would. It will do that sort of thing here on the ground, of course, as you spin it. But of course, the friction of the jack against the platform it's sitting on begins to slow it down, and it will eventually fall over. It spun for a great deal of time in zero gravity because it had no friction against a surface that it was resting on. Of course, in zero gravity you also have the problem of placing yourself so that you may reach the jacks so that you can play the game without floating away yourself. If you toss the jacks, toss the ball, and then lost your foothold on the ground, if you were no longer stabilized, you simply went floating around the jacks and couldn't really play the game at all. So there were some logistics with getting yourself placed in such a way that you were stable enough to reach the jacks, to catch the ball as it came back within your grasp, and to be able to play the game in that sort of an environment.
Another project that we wanted to attempt was juggling in space. Now, I'm really an amateur juggler. I have never really done very much juggling. About 3 years ago or so, somebody gave me a set of juggling bags for Christmas, and I threw them around the house a lot. I had to chase them underneath the furniture, and they rolled around. And I discovered very early on that if you're going to do juggling, what you don't want to start out with is balls. Balls, of course, are what the pros use, and clubs and things like that. But the trouble with balls is when you drop them, they roll underneath everything, and you really have to go chase them around all the time. These little penguins are stuffed with some sort of beanbag sort of thing, and they're much better. First of all, they don't roll around when you drop them, and second of all, they're easier to catch. So when you first start out juggling, the idea is to throw an object from one hand to another, just one at a time. In fact, when they start out, what they ask you to do is throw it from one hand and just not even try and catch it and let it fall down. I quickly mastered that, and even you guys can do that. And then you progress on up to 3, and some folks are way above that in the order of 5, 7, and 9, and I've even heard of people being able to juggle 10 different objects at once. In 1G, that's really tough. In 0G, however, it's not quite so difficult. The real problem in 0G is positioning the objects, in that you get them in some position with very little force and very little velocity in any direction, and letting go of it so that it stays in that position is the real problem. Okay, so 1G juggling is a simple matter of tossing an object from one hand to another. Okay, something like this. It's tough to see against that light, Joe. And then, I guess if you can do one hand at a time, or either hand, and switch back and forth, that's kind of a fun thing to do also. And this can go on and on with various sorts of manipulations around your back and over your head and between your legs and that sort of stuff, but that's for good guys. And for us amateurs, we have a lot of trouble with that sort of thing. So, now how do you think these guys are going to behave in 0G? When I toss him up, the penguin up, or actually what we used were apples and oranges, because that's what we happen to have. We didn't have any penguins as part of the toy kit because we have some flammability standards and some problems with that. When you toss him up in 0G, what's going to happen? Right, he's going to just keep on going. So you can't toss him up and allow gravity to pull him back down into your other hand like we can in 1G. So we tried positioning a actual circle, a circular array of objects, in this case fruit, in a circular array, and just replacing one object with another one and actually shifting them around, which is a manipulation, if you will, and a form of juggling, although not juggling in its purest sense. What we finally ended up doing in a juggling sense with 3 objects was tossing them from hand to hand in this direction, back and forth, trying not to impart any vertical velocity to them at all, merely a horizontal velocity, so that you could at any single time have one object in one hand or several objects moving back and forth in front of you in a horizontal direction rather than getting the vertical direction. Keeping control of them, as you can see from the film, is a real problem. If you ever let them get away, then you end up reaching all over the place, as you saw me do with these little penguins, reaching all over the place trying to recover them, and you end up with a disaster. The real problem with our fruit juggling, of course, was that I had to do it very early on in the flight, and I didn't get a whole lot of practice in order to perfect the technique, because by the end of the flight, all my props had disappeared. The crew ate them.
I guess my personally favorite toy in space were these little magnetic marbles. the little plastic marbles, and they have bar magnets inside, so each magnet has a little north and south pole, and they stick together. As you can see now with weight on them. Now notice I'm pushing the wrong pole up, so they don't want to stick together. It's pushing the magnet out of the way. So I'll turn it upside down, and now we get a nice sticking force there. There's a limit to how many of these I can support. And that's about it. You notice now the top magnet is pulling away. It can't support the weight. Well, just barely, I guess it can support the weight of those 5. Let's see what happens if I try to put on the 6th. That was about it. It's too much weight. Well, of course, in space you don't have that weight, so you can really make a chain of as many marbles as you want and sort of pull them all around the cabin, which I found kind of fun. In fact, we even put the first of the marbles on a string, and then I could sort of lead them around like a little pet snake of magnetic marbles, and in fact swing them around. Now here's an interesting problem for you. If you swing the marbles around, of course there's different amount of force on the different marbles because they're going at different speeds at different distances from the center. The one at the outside is going much faster, so you may think that feels more force than the one on the inside. The question is, if you get going fast enough, of course, the marbles eventually are going to come apart because the forces pulling them apart are stronger than the magnetic forces. The question is, where is the string going to break? At the outside or at the center? That's something to think about. There's some other things you can do. You can put one marble sitting here in the middle and roll another marble at it, and you can actually see the magnetic interaction. Now the problem here on the ground, there you notice how one marble captures the other, and if I throw it slightly off center, they start swinging around one another. The problem is that there's rolling friction between the marbles and whatever surface they're on, and therefore you can get a little bit of motion, but they very quickly come to a stop. I can do other neat things. I can get the marbles in little rings. I knew before going up into space that these rings would hold together, and I thought it would be interesting to see what happened when you threw rings at one another and got them to interact. Now the problem on the ground is there's so much friction here that you use up so much of the energy just in the sliding that, well, here it's sort of stuck together, but they really don't do anything. They've used up all their energy, whereas in space, when they came together, they were actually dynamic, and they would oscillate, and depending on how they actually hit, sometimes they would come together and retain their individual identities, or sometimes they would actually unite into one large ring. It was really quite fascinating watching the dynamics of these marbles interacting. And I could get a chain of marbles and take another marble, roll it into the chain. It can get captured. But what you don't see, because of the friction, which really brings the system to a stop, is that when this marble comes onto the end, it actually brings a certain amount of angular momentum into the system. And if it weren't for the friction, it would start this whole thing rotating around. And that, in fact, you see in space very clearly. In addition, if you could take a single marble and hit the chain at various places, you could also set up certain oscillations, which in some cases cause the chain to form up into a circle. In other cases, it just caused the extra marble to form on as an outsider to the circle, and you can actually build up a little tail on the circle. All these things you can see in space because the dynamics is so clear and completely uncomplicated by the frictional forces which you have when these marbles are rolling around on the Earth.
Okay, our unofficial crew mascot on this flight was a pink flipping mouse, and we nicknamed him Rat Stuff to see if he really did have the rat stuff to fly in space. The mouse is a wind-up toy depending on a spring force, an action and a reaction, and a balance in order to enable him to do, in one gravity at least, backwards flips, such as this. Having watched Rat Stuff do a few flips on Earth and seeing how he goes about doing his trick here, we had various thoughts about what might happen to him in space. First of all, we knew that there would be a problem maintaining him on a surface, because in zero gravity he's not going to sit still here on this particular surface and do his flips. He must be able to push against something as well as exert a force with his feet and the spring that's inside of him in order to do his flip. Without that, of course, he would just hover out in the air here, merely flipping his feet around and not getting anywhere. So attaching him to a surface became a problem, because in zero gravity he won't sit on the floor or the wall or the ceiling. He would just hang around a very small distance away from any particular surface. We tried a couple different ways to get him to adhere to a surface. Thinking that surface tension might work, we have some hand cream that's part of the personal hygiene kit on board the orbiter, and by smearing a little bit of hand cream on this flat surface on between Rat Stuff's feet here, we thought we might be able to get him to actually stick to a vertical surface, either a wall or a ceiling or perhaps even the floor. So I started out by putting a little bit of hand cream on the flat surface here, and he still wouldn't stick. It's a problem because whenever I would push him against something, of course, I would either push myself away or push him away. The wall, of course, wouldn't move, so by pushing on the wall with Rat Stuff, what I'm really doing is pushing him away, trying to get him to stick against the wall, and I'm exerting a force on the wall, which the wall exerts backwards, of course, and that would actually push him away since the wall doesn't give. I finally did get him to stick to a surface so that we could see what he would do in zero gravity by putting a rather large amount, what I thought a rather large amount of hand cream on the bottom of his feet here. We also tried some of the electrode gel that was used as part of the echocardiogram experiment, which also worked, but I had to put nearly a blob about the size of a pencil eraser on there to get him to stick. Later on in the flight, after he did some of his flips across the middeck, we attempted to put some Velcro on the bottom, some hook Velcro on the bottom of his feet, and then attach him to the pile Velcro that's mounted at various places around the orbiter to see if he would flip off of that. We had some initial doubts as to whether that would work because of the softness of the pile Velcro, whether or not he could exert enough force to flip away. And that's exactly what happened initially. We had a little strip that covered this whole area around his base here in Velcro, and he just sort of stood there and flipped against the soft pile Velcro and wouldn't detach himself. We finally did get it to work by cutting down on the amount of Velcro attached to his feet, down to the point where we only had 3 or 4 hooks out of a whole piece of Velcro that went across there. So as you know, that Velcro has many little hooks. They're all gathered together in a rather tight pattern. What we had to do was kept cutting it away and cutting it away and cutting it away with the scissors and a knife until we were down to the point where there were only 3 or 4 of those little hooks sticking out, which actually enabled him to hang on to a piece of pile Velcro, but not hang on with enough force that he wouldn't flip away. We attached him to a wall. He did a flip, continued end over end, completely across the middeck. And as you see in the film, taken in space, there he goes, completely across the middeck and out of your picture. And that tended to be the primary mode in which Rat Stuff would do his trick in space. He would push off either the Velcro, the bulkhead, or the deck, or the checklist that we had him mounted on, and go off in a perfectly straight direction, spinning at a rather rapid rate. The spin, of course, induced by the fact that he tries to do a flip against the surface that he's attached to, thereby setting up the rotational motion, the translational motion as a result of the force that he exerts against whatever surface he happened to be positioned against. So there you have it, Rat Stuff He really flipped out over this flight.
This is a toy gyroscope. It's really a top in another form. What I do here is I get this spinning gold-colored mass, and then the gyroscope displays gyroscopic stability. I pull on the string to get the mass going, and I do the same in zero gravity as I do here on the Earth. One item is that in zero gravity, unlike here, that the friction at this bearing point and this bearing point causes this whole gimbal that the gyroscope is spinning in to rotate. So not only do I have just a little piece in here spinning, but I have the whole thing rotating. It's very interesting to watch the gyroscopic stabilities of the gyro in zero gravity, because I can just suspend it out in front of me in space and push on it to see how it maintains its orientation. Okay, you can see how it moves around, but it still maintains its orientation in space. Of course, this is a graphic description or demonstration of why we spin our satellites. You can see even though I put a force on it, it doesn't fall over. It maintains its orientation. And so if this were a satellite and we were deploying it from the bay, even though something would happen to try to disturb it, it would maintain its original launch orientation. And if I have a platform, it'll maintain its orientation with respect to the stars, so I can move a spacecraft around it and I still have a platform that maintains its original orientation, so I know what that orientation is. In the space film, I had one instance where I had the gyroscope spinning and I moved around the gyroscope. And imagine that as being a spacecraft moving around, maneuvering in space, and you still have the gyroscope that gives your orientation, and so is a reference for attitude maneuvers. Here, when the gyroscope slows down, it eventually will fall over. That's because there's gravity pulling on the different parts of the gyroscope. In space, when the gyroscope slows down, it doesn't fall over because there is no gravity pulling on it. In space, I found that I could push the gyroscope with a string, and that was a convenient way of maneuvering it around and showing its stability. I can do the same thing here. One of the items that I demonstrated while in space was the gyroscopic action of the gyroscope on the end of a string as I was twirling it around. First, I did not spin the gyroscope, and you'll see that it maintains its orientation of having the axis of spin, what normally is the axis of spin of the gyroscope, aligned with the string, which is the centrifugal force as I spin the gyroscope around. See if this works. In space, when I had the gyroscope spinning, it would have some orientation, say this orientation here. And then even though I was spinning it, it maintained that same orientation as it went around in its arc. There was a force on it where the string is tied due to the centrifugal force of the spin, but the gyroscope was able to overcome that and maintain its stable orientation in space. Well, you can see it doesn't do nearly as good a job as it did in space, but it still does maintain some of its orientation. My name is Bo Bobko. and I was the commander of the 51D mission. That was the flight on which we took some simple toys to be able to demonstrate the physical characteristics that they intrinsically have, and also to be able to demonstrate their characteristics in the zero-G environment, in the environment of space. The toys that I chose were, one was a top, which is really a gyroscope in a toy manner, and the gyroscope itself in a toy fashion. The top, of course, displays the physical principle of gyroscopic stability, which is what we wanted to show. We in the space program are very dependent on gyroscopic stability because we use it in our navigation, and we of course use it in the spin stabilization of things such as satellites. You'll notice that when we launch many of the satellites, that as they leave the payload bay, they're spun, and that's so that they will maintain their orientation in space. If I take a simple top such as this one and I don't spin it, it tumbles like any other object would in the gravity environment here on Earth. But if I spin the top, it displays gyroscopic stability. That is, it maintains its orientation in space, so that if I push on it, it doesn't fall over, it moves, but retains its stability, it retains its pointing in the original spin axis. One of the problems that I envisioned before I went into space and found was actually a problem there, was that as I spin the top here, as I pull the plunger up and down, gravity holds the main body of the top on the surface. In space, of course, this didn't occur, so that when I pulled the plunger up, the top also came up. And you'll see on some of the space footage that I just held my fingers on the top of the top so that I could get it to spin. One characteristic of the spinning stability principle that was different on Earth and in space was that on Earth, as the top tends to slow down, it precesses. That means that the gravity vector, the force of gravity operates on it, and so it tends not to maintain its stability as we would expect it, but slows down and tends to fall over. Of course, in space, there is no gravity vector. So even stopped, the top will maintain its orientation unless there is some disturbing force on it. And so in space, as the top slows down, it maintains its orientation, which it would do even if it were not spinning. In space, the only time it will precess, the only time it will move, of course, is when you put some force onto the top.
This is a little magnetic wheel-o. The magnet on the axis of the wheel holds on to the metal of the track, and therefore you can actually get the thing moving around the track. Now, the way we normally get it working on the Earth is to just tip it down and let gravity start it going. Now, obviously, we're not going to be able to do that up in space, so there has to be some other way of making it move. And I worked with this before the flight to see if I could, by flipping it back and forth, use the centrifugal force, which will tend to push the wheel to the outside to get it going, sort of like this. So you do have a force available using the centrifugal force, and we can get it going. So I figured, since I could do that on the Earth, I was pretty confident I could do it up in space. And the other thing, of course, that's going to be different on Earth is when you stop the thing and just let it run down on Earth, there's frictional forces which eventually stop the motion. And of course, it always comes to a stop at the lowest point on the Earth. Now, that clearly is not going to happen in space. The frictional forces are still going to be there in space, but it can clearly come to a stop anywhere, and I demonstrated this. Now, the one other thing which I wanted to try up in space, and for this there was no way I could test it out on the Earth, was just get the thing spinning and then let go of it, and of course it will stay there, but it's governed by its own dynamics. Now, I guess I was maybe sort of expecting to see this sort of thing where you have a certain rotational angular momentum, get the things spinning around one another. Well, in fact, that didn't happen, and what we actually saw when the thing was moving around, depending on whether the wheel was moving up or down, it had a certain linear momentum. So when I let go of it, if the wheel was actually moving in this direction, even though the track itself wasn't moving, when I let go of it, as soon as the wheel got to the end and turned around, it actually then started the track going off in this direction. And so the whole thing, although it looked like it was steady when I let go of it, pretty soon it would be moving off in some direction in the shuttle. And I think that's a nice demonstration of the conservation of momentum. All in all, no great surprises, but it was kind of fun to play with for a little while.
Hi, I'm Dave Griggs, and this is a yo-yo. Now, the yo-yo's been around for a long time, at least several hundred years, and it demonstrates two physical properties that are very unique. Both of them have to do with motion. The first is rotational motion, and that is that the yo-yo actually rotates about a spin axis, which is the axle of the yo-yo, and it also translates. And the translation is that it goes straight down or straight out if I happen to throw it straight out, or straight up if I happen to throw it straight up. Now, the yo-yo depends to some degree upon rotation to keep it steady in space. That is, if I just drop it very slowly, it'll have a tendency to turn on its string. However, if I throw it down very rapidly, it'll go down very straight, as an example like that. Now, what you just saw a minute ago was a sleeping yo-yo, which is unique in that you can make the mass of the yo-yo actually stay at the bottom of the string. Now, this trick couldn't be done in space, and I'll tell you why in just a moment, but let's look at that one more time. You see, the mass stays at the end of the string, and when I give it a little jerk, it comes back up into the hand again. Now, in space, because every time I would throw the mass of the yo-yo out, it would tend to, once it got to the end of the string, it would stretch the string ever so slightly and rebound, and in that rebound process, the string would get loose on the axle, and then by friction would wind itself back up again. Now you'll see here on the Earth's surface, when I throw it down, not quite like that. The way I get it up is I actually loosen the string a little bit on the axle and get it to come back up in the hand again. Okay, one of the unique things about space, of course, is that there isn't any gravity there. And that enables you to use the yo-yo much slower than you can on the Earth's surface. Now, on the Earth's surface, of course, you have to throw the yo-yo fast enough that when it gets to the end of the string, it has enough rebound motion that it can work itself back up, lift its own weight back up the string, lift its own weight against gravity back up the string. Now, in space, without gravity, you can actually throw the yo-yo extremely slowly, and it performs all the rotational and translational motions that you anticipate or expect it to do. And you'll see in some of the space footage that I'm actually throwing the yo-yo out away from me at a very, very slow velocity. And without gravity, of course, it doesn't sink down. It merely goes straight out and then comes straight back. Now, I'll demonstrate that here on the Earth's surface. You'll see that if I throw it out very slowly, the yo-yo will drop down and won't have enough momentum to actually climb back up the string. As an example, you'll see that it has a tendency to fall back down. But if you throw it out very fast, you can get it to come straight back to your hand. Of course, in space, as I mentioned a moment ago, you can do the tricks extremely slowly, and what this enables you to do is to actually see, observe the dynamics of the mass of the yo and the string, observe the interaction of those two objects, the string and the mass of the yo, and actually make corrections for any slight errors that you may have initiated into the trick. Now, on the Earth's surface, unfortunately, you can't do that because, once again, you have to do the tricks very fast in order to maintain control of the mass. One of the tricks I did in space is called the flying saucer. Now, the flying saucer is merely where you take the yo-yo and instead of having it unspin in a plane such as this, you have it unspin in the horizontal plane, going straight out away from the body, like so. Now, that's a difficult trick to do on the Earth's surface because of the gravitational field having a tendency, once again, to pull the yo-yo down, and when the yo-yo starts to get pulled down, the string has a tendency to come out of its track, causing the yo-yo to become unstable. But without gravity, of course, you can throw the yo-yo out very, very slowly, and it'll stay absolutely parallel with the string as it goes out, reach the end of the string, and come very neatly right back up into your hand. Now, let me try it here on the Earth's surface, and I'll show you the problems. What happens if you don't do it slow, or if you don't do it fast enough, excuse me. You see, it falls down, the string becomes entangled in the track, and the yo-yo becomes unstable. Now, if you do it fast enough, you can actually get the yo-yo to go out and come straight back in your hand, once again in the horizontal plane, like so. There was a couple other tricks that I did. One of them was what we call a shooting star. And generally on the Earth's surface, the shooting star is done in the vertical plane, where we release the yo-yo as it's going up. We release the string from your finger, and the yo-yo then just climbs up, depending on how hard you threw it, and the string continues to wind around the axle so that the time it reaches the apex of its travel, the yo-yo and the string are all wound up, then it drops back down in your hand. Now, in space, since the confinement of the middeck prevented us from throwing the yo-yo straight up, I did it in the horizontal plane. Once again, no gravity to pull the yo-yo down. I did it in the horizontal plane across the length of the middeck, which is about 8 feet long. And you'll observe that during that motion of the yo-yo going across the middeck, that it did not sink at all because of the lack of gravity. And that was the shooting star, which is a interesting trick and a fun one to do. Shooting the moon is a very interesting trick. It's an extremely difficult, advanced trick to perform on the Earth's surface. Once again, because gravity has a tendency to work against the person that's playing with the yo-yo. Now, the trick consists of throwing the yo-yo out away from the body, bringing it back, and as he comes back, you flip it up around the wrist, straight up, and back down into the palm again. Obviously, gravity is working against you while you're playing this trick. But in space, without gravity, it is extremely easy to perform the trick. You can do it relatively slow and observe the actual dynamics between the yo-yo and the mass and your hand and make the corrections that are required in order to effect the trick properly. Okay, let's try the trick here on the Earth's surface. And you'll probably see that I may have some difficulty with it, and I may not even be able to do it. Here we go. Close to it. But you'll observe in the space film how easy it was to do. Okay, kids, that pretty well does it for the yo-yo. We certainly had fun with it in space, and I know you'll have lots of fun with it here on the Earth's surface. Happy yo-ing to you.
Okay, I have here a little wind-up car. Now, on the Earth, it's a very simple little toy. You just push it back and forth to wind up the spring, let go, and whammo, it's off. And it runs quite nicely. Of course, the spring makes the wheels turn. Gravity holds it onto the surface, and therefore you have friction between the wheels and the surface, and that makes it go forward. Now the problem in space is that without any weight to hold the car down on the surface, when you wind it up and you let go, essentially the wheels just turn the same way as if I'm holding it up in the air. There's nothing to hold it down. There's no force pushing it down, and therefore there's no friction to allow a force to push the car forward. We have to think about, is there any way that we can get it to work up there? Well, what you really need is some way to get a force between the wheels and a surface. And in fact, there is a way that we can do that in space, and it's using centrifugal force, which exists in orbit just like it does on the ground. So I have a little round track here, and if I can get the car running around fast enough, because of course the amount of centrifugal force depends on the speed. The faster it's going, the faster the speed, the greater the centrifugal force will be. So if I can get it going fast enough, then it should hold into the track. Let me see if I can get this going. Of course, it'll go around for a while, and then it's going to run out of force. It's going to slow down, and eventually it will fall out of the track. There we go. And eventually it falls out. Let's see if I can get that going again. Now, the big difference in space is going to be there's no weight to the car, so there's not going to be anything pulling it out from the track. And therefore, what really ought to happen is it should just, as it goes slower and slower, it should just basically come to a stop right inside the track. And eventually, just the little motions, because of course if I hold it, my hands are going to shake a little bit. And eventually it probably will just float out and go away. And in fact, that's exactly what happened. It behaved just as you expect, but visually, and I think this is one of the neat things about the toys in space, although we weren't surprised by the way this car behaved, visually you're so used to seeing the thing slow down and fall out of the track that when you actually see how it operates in a weightless free-fall environment, and you actually see the thing going around ever so slowly and still holding in the track, you become all that much more aware of how the centrifugal force operates. I think for the toys in general, being able to see things operate much more slowly gives you a very good idea of what the physical principles are that make these toys operate.
We also carried some science demonstration objects, commonly known as TOYS. This was done primarily to make some educational footage, which we can use and distribute to science teachers throughout the country. Here, Bo forgot to spin the gyroscope up, and somehow it just didn't stay stable. So we're going to give him another chance, and here he's going to get it spinning. There we go. Of course, the principle of gyroscopic stability has been around a long time. We use it for navigation. Our satellites use it when they come out of the cargo bay. But of course, without gravity and just being able to float it free here, you can study the behavior of the gyroscope and watch the way it moves around in a way that we never get a chance to do in laboratories on the Earth. I'm sure all of you have held a gyroscope on a string or on your fingers, and after a while, as it spins down, the force of gravity starts to torque it, and it starts to process around. Of course, that never happens in zero gravity. You can keep playing with it almost up to the moment where it is not spinning at all, and it still stays stable. In fact, it was just a constant source of fascination, all the different things you could do with these very ordinary devices. This is a little magnetic wheelo that I'm using. Normally on the Earth you start this with gravity. I found it was pretty easy to start it up using centrifugal force. This one, as long as I was holding it, behaved pretty much the way it did on the Earth. But as soon as you let it go, then it does all sorts of neat things. And here comes Mr. Yo-Yo. I've had a lot of discussions with physicist friends of mine about whether the yo-yo was going to work, and it worked fabulous. You could do it fast, you could do it slow, you could do it to the ceiling. That's the famous oi-oi. Dave did flying saucers around the moon. He's a real champ, and if they don't let him into the Yo-Yo Association of America, there's just no justice in the world. Putting the jacks here, there was constant danger of massive explosions if the ball came back in the wrong place. We managed to go through without ever losing the jacks, and although it's not on film, Ray did manage to do her 12sies by the end of the flight. If you let a paper airplane just float, it's pretty much carried away by the air currents in the shuttle, as you see here. And so it really doesn't take very much force just to start it on the most beautiful flight that you've ever seen of any paper glider.
Hope you like our home movies so far. The paddle ball behaved a lot like it does on Earth in that you can paddle it in nearly any direction if you're clever enough. I'm not sure I am clever enough to keep it going in each direction. And, as you can see here. So the ins and outs, ups and downs were about the same. It's a little harder to do, to do this trick on Earth. The straightforward sort of paddleball operation is much slower and it's much easier. This one is a little tougher. Jeff has here some magnetic marbles. I'm not sure how you shoot marbles in space because it's a little hard to keep them in that ring. But your shooter seems to work fine. It joins right up with them all, and it forms into a toroid, as you might expect, with the magnetic lines and the magnetism that's inherent in the marbles. If you watch carefully now, on not this one, but the one after this, as Jeff sails the marble past after he repositions his ring here with its little tail, and relative to the horizontal lines on the bulkhead behind him, watch what this marble does. See it curve upward as the magnetic lines of force pass by the others. And here's our unofficial mascot. You might say he flipped out over this. Rat stuff really had it. The slinky, without the sag that you have to contend with in 1G, behaved pretty much the same as it does in 1G. You can start to see that, of course, they've set up a sine wave oscillation here, which continues to be reflected back and forth, and now a double one or perhaps a triple, and perhaps within there you can also see the standing waves reflected back and forth. The centrifugal force, of course, keeps this little car going around its track. On Earth, when it gets to the top, it would, of course, fall out.